Good morning, and congratulations to all of you on the World Meteorological Day. And thanks to this World Meteorological Day today, we don't even have a choice, this morning at least, we don't even have a choice about the language, because we also welcome the European Meteorological Society, so everybody who's watching now online via YouTube, because the European, our partner organization, the EMS, has asked us to give a glimpse into the DACH MeteorologieTagung to celebrate the World Meteorological Day across Europe. And Christoph Schär kindly agreed that we can broadcast his keynote lecture via YouTube. So I don't know who, but I guess that many colleagues across Europe are watching either now or during the day. And let me first of all thank Christoph Schär for accepting the invitation to give a keynote lecture at our meeting today. Christoph has a degree in physics from the ETH Zurich and a PhD then in atmospheric sciences. Has held positions or worked later on in research positions at Yale University and also at the renowned, center or mecca for cloud physics at the University of Washington in Seattle. And if I'm not mistaken, celebrates his 30th anniversary as a professor at the ETH Zurich later this year. Christoph, as many of you of course know, is probably in Europe at least, most influential pioneer when it comes to high resolution or storm resolving, as some of us call them now, simulations at the large scale. And I think, or many of us, I guess, think it is urgent time that we make some move in climate modeling. So perhaps climate modeling hasn't seen step change improvements in a couple of years. And I think we are seeing or witnessing soon the advent of a new generation. And this is not least thanks to decades now long of work by Christoph. And so he shares today with us some of his experiences from this endeavor. Thank you very much.
Thank you. Thank you very much, Johannes. I hope you can hear me. Okay. Once again, thank you very much, Johannes, for this very kind introduction. It's a pleasure to be here. I have never been in Leipzig before. It's a wonderful town. And I must say I was very touched when Johannes introduced Friederike last night and saying this statement, unfortunately, weather is not the prime topic in our discussion, and that's really true. I also noticed that the flag of Leipzig carries actually virtually the same colors as the flag of the Ukraine. And so let's hope that this situation improves. So I should mention, maybe before I start my courses, it's a long list. I should particularly mention Roy Cui, Christoph Heim, Nicolina Bahn, of course, and Marie-Estelle Demery. You will see some results of them. But I start here with a look back, namely something that a very old paper, 1975. It is this paper, Manabe and Wetherald, was actually the first 2x CO2 experiment published with a three-dimensional model. And this had a terrible simplification from today's point of view, atmosphere only, idealized distribution of land and sea, and so on. You can read here the details. The resolution was 450 kilometers, only nine computational levels. But despite that, actually, the main results that this paper achieved were outstanding. I'm afraid there is a problem with one of the diagrams to the right. But the main point is really that these 5 or so points that are listed here have been new results, or maybe one has been half new. 4.5 have been completely new and have been confirmed by observations that followed up. So it's really an important point. Now, it's also a good argument to start this lecture, because if you look at the computing power that Manabe and Wetherald used in 1975, so they did their work on IBM Stretch, which was actually the predecessor of the IBM success story. This Stretch was actually an economic disaster. The cost of it was almost $8 million at the time, so 60 million today. and they sold only a few machines, and Wetherald and Manabe used one of them, and this was the first supercomputer that supported 1 megaflop, meaning 1 million operations per second. And of course, today we have much larger computers. In Switzerland, we use often the Pitt Stein, which is in our National Supercomputing Center. But all of you have a supercomputer in your pocket. So if you have an iPhone 11, this is about, what is it? It is 7 orders of magnitude faster than the IBM Stretch used by Wetherald and Manabe. And it's only maybe a factor 1,000 or 10,000 below what we have in today's big supercomputers.
Can you speak up, please, so the microphone closer?
Okay, thanks. So,
Is it loud enough in the back? Or should we do something? It's loud enough.
okay, I'll try to speak a little louder. I have a big, weak voice. Okay, now it's improving. Thanks a lot. Yeah. Okay, now with this diagram, one can make an interesting thought experiment, namely what would happen if we assume that they would run their code today on today's supercomputers. So we can scale their model to today's supercomputers and assume optimal use of hardware and ask the question, at what resolution would they be operating today? And if you do that, you come to the conclusion that they would run their model at 500 meter spatial resolution with 150 layers. And so one wonders, because we haven't come that far. So we are not yet there. And of course, there are different reasons. One of them is that it's very hard to use these modern supercomputers. Now, of course, we should ask, how can we come to the high resolution? And in this diagram, you see the basic, actually, one consideration of that, where on the horizontal axis, you see the domain size that is covered by a model. And on the vertical axis, you see the grid spacing. And so if we say 1 kilometer global is our target, then it's that symbol here. And of course, one can approach this target on this axis, namely increase the resolution of current climate models. But one can also approach it on this axis, increase the domain size of high-resolution regional models. And if you look at the literature, that is really what is happening or has happened in the last decades. So these are some of the publications. And so you see that roughly in 12 years, so 12 years ago, this publication from Keynote et al. Covered 0.01% of the Earth's surface, and then was the largest domain that was run in climate mode. And today we are approaching 10%. And similar things happened with GCMs, which have the resolution of these GCMs has been dramatically refined by roughly 1.5 to 2 orders of magnitude. And if, in addition, you plot those simulations that cannot be considered climate simulations because they are only a week long or 2 months long, then you really fill also the target area of this diagram, meaning we are almost there. But of course, there is still a long way to go. I should actually add one more point. So I will show you today also some simulations from Christoph Schär, which are carried out on a very large domain in the Atlantic. Now, why actually should we go for kilometer resolution models? There are kind of 3 arguments. First, we are able to have a much improved representation of the water cycle. We have heard of that already yesterday. We can represent convective precipitation, extreme events, organization of convective cells in ways which are fundamentally not possible with parameterized models. Second, we can have more resolved topography, coastlines, land surface properties. So that will improve actually gravity wave, mountain circulation, land atmosphere exchange. And last, we can hope that we have improved representation of the cloud cover, and that has a potentially important implication for the understanding of cloud feedbacks, climate sensitivity, and climate change. Now, essentially, the introduction of kilometer resolution allows us to switch off 2 critical parameterization schemes, namely deep convection and gravity wave drag. And you see here from this diagram also why we need this high resolution, because these are just narrow scales in the convective cells. So I should maybe say one word of how we do our simulation. So I should maybe first say that we are using this GPU computer, where actually the computational tasks are done on a GPU or on GPUs, on a large number of GPUs rather than on CPUs. And the model we are using is the Cosmo model, and the effort actually to transport this model to this GPU computer has been tremendous. It has been between 10 and 20 person years. And so you see here how this has been done. I'll say a little bit more about that later. And this model is also used for operational numerical weather prediction. Now, the simulation domains that we typically use over Europe and the Alpine region are shown here. They cover a large fraction of Europe, and we use even larger domains over the Atlantic. So I will look into two topics more specifically. The first is severe weather associated with thunderstorms, meaning really here heavy precipitation, hail, and lightning. And the motivation, or one of the motivations, are floods like the one in the Ahrtal. You see here a picture of the devastation that happened on the 15th of July last year. You see here also actually the runoff gorge, the record of the runoff gorge, and the last point that you see here, the last data point taken in the evening of the 14th, is actually the last point that was communicated in real time. I'm not completely sure whether the station was destroyed thereafter or whether the data is actually available. And you see here also some analysis done by the German Weather Service, so you can actually see these are small-scale events that involve embedded convection. And so we know that kilometer resolution improves. I show here one diagram in an early study of this type, where we see now at the moment the mean diurnal cycle over the summer validated against 62 actually rain gauge stations in Switzerland. And so you see that actually the 12 kilometer simulation with parameterized convection has a serious problem. You see it most pronounced in the wet hour frequency, overestimation of precipitation frequency by more than a factor 2. And most of these problems, they disappear simply by switching to 2 kilometers. And so there is a big potential in this resolution, these resolutions to fundamentally change the behavior of the models. And it's not only the improvement of the diurnal cycle, it's also the improvement of the extremes, and you can go to higher time scales. Here a diagram that is based on this so-called Cortex FPS setup, or experiment, where we have now 23 model simulations at 2 kilometers, covering the larger Alpine region for a duration of 10 years. So it's really long enough to do with an evaluation of the statistics. And this is done here, where we compare observations in the left-hand column against the high-resolution simulations with explicit convection, and against the lower resolution simulation with parameterized convection. And you can see here the three rows: intensity of precipitation, mean intensity, then the frequency of precipitation, and the heavy precipitation events in terms of percentiles, the 99th percentiles. And you can really see what happens here. So the 12 kilometer simulation has a dramatic underestimation of mean intensity and an overestimation of precipitation frequency, meaning it rains far too often, but the amounts are too small. And this is a characteristic of lower resolution precipitation simulation. It's also referred to as the drizzle problem. These models have the tendency to produce lots of often precipitation at small intensity. Now, in the lowest panels, you see the magnitude of the larger event. So this is the 99th percentiles, and the transition between the orange-red colors to the green colors is as 12 millimeter per hour. So these are sizable precipitation amount, and you can see that these precipitation amounts are not reached in the 12 kilometer simulations. This is hourly precipitation, important, not reached in the 12 kilometer simulation, but the 2 kilometer simulations has a reasonable success in representing the simulations. Now this was hourly data. Now one can do this also at higher temporal resolution. So again, this is now the statistics for hourly events, and what we do here is we plot the observed percentiles versus the simulated percentiles for a 10-year integration, and the different colors of the dots are the different percentile levels considered, and the different dots represent also different stations. And so you can see that here we are not perfect, but reasonably close to the one-to-one line. Actually, you can see that this model at this resolution and time scale underestimates to some extent the heavy precipitation events. Now the point to make is one can really refine this analysis and go from the 1 hour to the 30 minutes to the 10 minutes time scale, and finds that even at 10 minutes there is a reasonable representation of the precipitation statistics. We see a little bit of fall off here, so we are kind of probably losing the ability to do this at 5 minutes or at 2 minutes, but up to 10 minutes, we have a reasonable chance of representing the precipitation statistics. And this is, of course, of central importance because it's this short-term precipitation that are causing many urban floods in particular, where the runoff systems are not able to capture these kind of large precipitation amounts. Now, one can also look into the projections, and that is done here, where we look at the change in intensity of high precipitation events, and the precipitation events are listed here as inverse return period, so it's basically events per year that we have in the control record. And so you can see that all these, irrespective of the accumulation period, actually the results signal an increase with the warming, and the warming has been here expressed as change in percent per Kelvin regional warming. So if we look at here something like 5-6%, and you account for a warming of 4 degrees, that would actually give an increase of 25 or so %. Now one can interpret that, and actually it's kind of interesting and fascinating that it appears that first of all the intensity increase is more pronounced with the heavy events, with the one on the right-hand side. But second, also, we haven't found a case where we can say that clearly we have an increase that exceeds the Clausius-Clapeyron scaling. So it looks like the Clausius-Clapeyron scaling, which it is such the measure of the saturation vapor pressure, reaches that point. Now, the Clausius-Clapeyron scaling, I should here show a little bit. So Clausius-Clapeyron, actually Rudolf Clausius, he was a German physicist, and he is very well known also for his other contributions to physics. This is the Clausius-Clapeyron relations, the equations that he derived. And as he spent some time in Zurich, I have the pleasure to cross this kind of Clausiusstrasse every morning when I walk up from the railway stations to ETH. Now, we looked here at heavy events. There is, of course, the question, is 1 kilometer, roughly 1 kilometer resolution, is that sufficient? And so we have looked into that, and so one can here distinguish, one has to distinguish two terms. The one is structural convergence, where we really look at the statistics of the cloud ensembles, meaning really look at the spacing and the size of individual clouds. But we can also look at, not sure what happened. We can also look at, sorry, missing that here. We can also look at the bulk convergence, where we actually look at the area averaged bulk effect over some grid box, and shown here in a perspective fashion. So we look at the heating and moistening in a cloud layer. And when doing so, one finds that first there is lack of structural convergence. You see this here where we plot the relative frequency of cloud areas as a function for 5 resolution. So this would be 500 meter resolution, and this would be 8 kilometer. So if we had structural convergence, we would see one line. That's not the case. Rather, actually, when we double the resolution, we change the cloud area statistically by a factor of 4, meaning really the cloud area, the size of the clouds, is determined by resolution. So we do not have structural convergence. But what we do have is or close bulk convergence. What we do here is actually we look at the statistics of up and down drafts, namely the relative frequency of convective mass fluxes. And you can see that if we go from 8 kilometer, the black curve, to the green, to the 2, then increasingly we approach this kind of curve, meaning we reach, we see bulk convergence. That means the convective mass flux becomes roughly independent of resolution, the statistics of it. And this is a very nice property. We are looking at some of that also now for cloud characteristics in the tropics and find similar results. Now, second, a brief comment or intermediate comment, Zwischenfrage in German, concerns hail. And so this is one of the things that we are trying to look now. We started it before this hailstorm, which happened 2 days before the R flood. And you can see, I mean, you can imagine what kind of power these hailstorms must have to cause this time of damage. And you can see from the greenish street what happened to the trees. So there were terrible wind gusts associated with the storm. The question is, can we use these models to look into that? And of course, hail in a changing climate is a complicated phenomenon. One can think of changes that increase the hail frequency and intensity, but one can also expect the opposite. So it might depend actually on the region what is happening. So here you see the two most important factors. So first of all, similar as with just convection, we will expect a moistening of the boundary layer. So that is highlighted here. We expect this moistening of the boundary layer, which will lead to higher cape, more instability, higher updraft strengths. But there are some other factors. An important one that is systematic as well is, of course, the vertical lifting of the melting level height, which is indicated here. So the melting level will raise, and that means depending on where you are, actually, there will be more space to melt the hailstones. So this might reduce the hail intensity, but might also actually lead to or change the spectrum of the hail intensity. There are other factors. We can have changes in wind speed. We know that actually the hodograph determines the storm type, whether we get a single cell storm or a rotating supercell thunderstorms. And there are other factors such as the lapse rate changes. We know that the lapse rate will change, and so actually this minus 40 degree isotherm will raise faster than the 0 degree isotherm, and this may also help to give changes in the distribution of hailstones. Now I show you here some recent results where we use actually simulations in a domain as shown here, and we do a systematic set of case studies to evaluate the potential. So what you see here is a validation of 8 case studies where we compare the Cosmo simulation. I should say important. Actually, this version of the Cosmo model has been equipped with 2 diagnostic tools named Hellcast and LPI, which allow us, without switching really to complicated microphysics, so it uses single moment bulk microphysics, it allows us actually to look into hail and lightning. And so here you see the validation of the hail. So the bluish color gives you the Cosmo hail. This is the probability of hail with size larger than 1. And the observation in the brownish color comes from a radar product called probability of hail, which has been developed by Meteor Swiss. And you can see there is not perfect match, but overall there is actually a reasonable representation of hail in these 8 cases. The overall characteristics are captured, but of course you should not expect, this is a highly chaotic system, we cannot expect that we have a one-to-one match between observation and simulation. The result for the lightning is also promising. So we see again the Cosmo model in bluish and the Linet observations in reddish, and you see that we have a reasonable overlap of the lightning, of the simulated lightning with the observed lightning. So we think that we can use this in climate change studies. So, and actually our next step is to do climate change simulations using the PGW methodology. I'll tell a little more about that in a moment. To look how lightning and hail might be changing on a European scale. Now the second point I want to make, or second topic I want to address in this presentation are tropical clouds and their role for climate change. And the motivation of that is, of course, not only from the fascinating cloud cover that we can observe in satellite pictures, but it's really the role that these cloud covers play in the global climate sensitivity and climate change. So here is the definition of the equilibrium climate sensitivity, the equilibrium warming for 2 times CO2. And according to the most recent IPCC report, this equilibrium climate sensitivity is between 2 and 5 degrees. And this is the confidence interval 90%. That means actually there is still a 5% chance that we have an equilibrium climate sensitivity above 5 degrees. And it would be nice to constrain this uncertainty. And so what I show you here is from a recent paper where we actually plot now for a large number of CMIP5 GCM, or each of these dots is a CMIP5 GCM, the equilibrium climate sensitivity as a function of the low cloud reflectance change expressed in percent per Kelvin. And you can see a clear correlation, meaning actually, as you would expect, if we have a reduction of clouds or an increase of clouds, then less solar energy reaches the planet and means the warming is not as pronounced. If we, on the other hand, have a reduction in cloud cover, then more solar energy reaches the planet and we have a high climate sensitivity. Which of these models are true, we don't know yet for sure, but if you look at recent observations, I think I don't have time to look into that. You rather see that for the Pacific at least, there has been a tendency in the last 20 years that we have a reduction in albedo, meaning we rather, from these observations, would expect something in this ballpark of the simulations. Now, we are using now our model on the argument, of course, is we would like to do, we cannot really do LES. This would be our favorite simulation mode, but LES would be too expensive. So we explore whether we can actually use kilometer resolution to simulate tropical clouds. And so this shows how this is meant. So with a GCM, this is plotted at scale and observed sequence over the Atlantic, and you can see that with, well, of course, a GCM, you have to parameterize everything, even at 10 kilometer, while maybe at 3 kilometer there is a chance to resolve some of these clouds. We have tried so in a domain that is very large, is this domain here, covering a large part of Africa and South America and the Atlantic. And what you see here is already a visualization, but I show you a little more in the next slide. I should mention that we think that we can come by with comparatively short simulations, a couple of years, because we are using the PGW approach, which essentially removes the internal variability, so we don't have to wait for 30 years to see statistical significance. So this is now a snapshot of the simulations, a visualization, and what you see here, so the whitish clouds, these are liquid water clouds. The thin ones here are ice clouds. The green color actually shows vegetation, soil moisture actually. And the colors that you see here is precipitation, and mostly is heavy precipitation. And so what you can actually see in this snapshot are these squall lines that form over the tropics in Africa and propagate westwards. And here you see a hurricane that has formed over the Atlantic. Now, it's a pity I cannot animate this. So it's actually a fascination to see how this model actually, it has never been told anything about squall lines or hurricanes. It only knows about the governing equations. And because the governing equations are so close to what happens in the atmosphere, actually this model generates the same kind of features that we are used from observations. Yeah, now we are doing these simulations. Oops, yeah. Here is a validation. So this is 3 years of simulation, and we validate cloud cover over different areas in the tropics. And so red is the Cosmos simulation at 3 kilometers. Blackish, grayish is the CIRES data, CMSAF data actually, and blue is the CMIP6 data. And you can see that even this is our first shot at the problem actually. No tuning of the internal of the annual cycle. You can see that actually Cosmo has a quite credible annual cycle. If you look, for instance, here, the trade wind cumulus, or also the cloud over the tropical Atlantic is, I should mention, we show here only long wave up. So actually outgoing long wave radiation, of course, we look also at the short wave radiation. So the model is not perfect, but overall this is a satisfactory agreement. And of course we haven't done much tuning, and that is ongoing now in other PhD. So we hope that we can further improve these results. Now I show you here the methodology how to do climate change. We have actually worked on this quite for a long time, and there are different flavors of this methodology. So what we use here actually is the control simulation is driven by the ERA5 reanalysis. And then we have a pseudo-global warming simulation, PGW, which is driven by a modulated ERA5 reanalysis. So this modulated, actually the ERA5 has been shifted so to some extent to account for climate change. And the climate change signal, the three-dimensional signal, is taken from the MPI model in this particular case. And so you see here how that is meant. And so, but of course, this information is only used at the lateral boundaries. So we trust this information at the lateral boundaries, but let the model run fully interactively inside the domain. Show you the kind of results that we get here. And I should mention these are preliminary results. So we can look at the cloud radiative feedback on this axis here for long wave, short wave, and total contributions. And what you see now is the distribution of the CMIP6 models. And now we can add the results from our model. So this would be the simulations, and the simulations is still running, so it has reached probably now a little further past May, but 2007. So we don't even have a year in this analysis. That shows how powerful that methodology is, how with comparatively simple simulations you can make a statement. And so for this case, what we actually find here is that the positive shortwave cloud radiative feedback that we find in the Cosmo model is similar to that in the CMIP6 model, or is close to the median of the CMIP6, while actually at long wave we observe a weaker feedback. So there is less long wave feedback in the Cosmo model. Of course, we haven't fully understood why that is the case, and that would mean for Cosmo we had a slightly stronger cloud feedback than for the CMIP6 mean. Of course, one can relate this to specific cloud type. And of course, I should point out that we should, these are very preliminary results, which I just showed to actually highlight the potential of this kind of methodology. Now, on the last question which we can ask, I hope I still have 5 minutes or so. Okay, so I hurried too much in that case. So, the last question that we can ask ourselves is, when can we actually expect to reach 1 kilometer global in global climate models? And again, we use this performance target which I mentioned previously. Say we would like to do we would like to work at the scale of 1 kilometer global, and would like to have 1 simulated year per day. Meaning you could do simulate 1 year in a wall clock day. And this is also roughly the speed run that is used at the big numerical weather prediction center. So that would also mean you could use these models for global NWP. Now, if you look at the past, and we have contributed to these questions, then one can actually say that the current models, they are, the current global models, they are about 100 to 250 times too slow for climate applications, meaning really doing big climate change simulations. Now, one can ask the question, when will we manage? How long do we have to wait? And we can go to this top 500 curve, which measures the speed of the supercomputers in teraflop, and you see actually this is an exponential growth. And so the best curve to look at actually is the sum of the 500 fastest supercomputers, because this gives us fairly smooth evolution. And what one sees here is there is actually a kink, roughly in 2013, and this kink is often related to the phrase, this is the end of Moore's law, or could be the end of Moore's law. So let's consider the future of computer power will follow this curve, and if we take now the time until 2013, then we have seen a factor 2 every 14 months. It's actually even faster than Moore's law initially stated, which is about a factor 1011 every 11 years. Now, unfortunately, as the Moore's law comes to an end, we have to look at the curve on the right-hand side, and there the increase is smaller, substantially smaller, namely a factor 2 in every 24 months, a factor 1000 every 20 years, and that would mean a factor 250 roughly every 16 years. That means if we just use our models, and wait until this larger supercomputer arrive, we would wait almost 2 decades. Now there is a chance to beat this. Questions, can we be faster with better coding strategies? And so the art here must really be that we must be able to exploit next generation supercomputers, which are not MPP CPU style systems, but which have much more complicated architecture. And of course, there are different approaches. We could use a Fortran with compiler directives. And actually, to a large part, the Cosmo model, except for the dynamical core, has followed this approach. So it is MPI, OpenMP, OpenACC. It leads to really unreadable codes because you have so many directives. And whenever you see a new computer, you get a headache because you have to change everything. The second approach is to write parts of the code using the processor's language. And so that has been used in the Cosmo model for the dynamical core, which actually has been written in CUDA. So part of the code is written in CUDA, and so, but even that is a headache because we are not sure how long CUDA will survive. So actually, this is a question. I think it's not sustainable to work on in this kind of structure. We have huge source codes. We have many changes in hardware. We have also many changes in the code. And so the third option would be to rewrite the model using what is called a domain-specific language. And I have one slide to highlight what that is. Domain-specific language, some of you might know. So it's actually really to separate, it's something like a new programming language, where as a climate scientist or as a domain scientist, we would only work in the reddish part. So we would have we would work with the mathematical model. We wouldn't look into hardware-dependent details, vectorization, parallelization, directives. We would really work with operators that are given by this language to us, for instance, operators such as a Laplacian or a gradient. And this part is referred to as the front end. And then the back end, which would of course be hardware dependent, would be rewritten whenever you move up to a new code. So this would be kind of would not be our task to do that. So this backend actually, it provides the executable for different target architectures and takes care of hardware dependencies. That means we can hope with this approach to have a stable code that will not change much, even if we switch from one hardware architecture to the next. And so there is actually a few great domain-specific languages are used, and in our community, the one that is most probably advanced is Grid Tools, which is a great a domain-specific language for doing stencils on grids. It has jointly been developed by CSCS, Meteor Swiss, and ETH, and it really provides these operations like Laplacians, gradients, divergence, or whatever you think. It has multiple interfaces, meaning it can be called from C++ or Python or other languages, and it has already been released. And since, so the applications that are available or under work, so the first one is the Cosmo model. It's probably still one of the few, if not the only model that entirely runs on GPUs. And it uses these grid tools in the dynamical cores. And there are now many projects actually which work with these grid tools, also meaning trying to extend grid tools. There are 3 global models that at least explore this approach, FV3 in the US, IFS FVM, the finite volume module from ECMWF model, and ICANN. These models are being considered using a version of grid tools. Now I should say, yeah, actually there are a number of backends are available for these tools. I should mention that we also think that as front end, we will be use Python. So in all these 3 approaches, the code is written in a Python-like language and uses Python or calls Python routines. And these Python routines are domain-specific routines, meaning they will be translated to the target architecture. And a number of backends are available. Yeah, I should mention actually that ETH, together with Meteor Swiss and CSCS, we have started this Exclaim project. And the main goal of this project is to rewrite ICANN using Python-based domain-specific languages. Of course, this project, we have a close collaboration with the MPI, with the DWD, and with other institutions using ICANN. And so we have a quite ambitious plan in this project. So this project has a duration of 6 years, and our goal is really to reach the 1 simulated year per day on a global scale with a coupled climate models within this project period. We will see whether this will happen. I have, if you want to know more about, you find a brochure about this project. And I have a brief summary. I think really the change that we will see in climate modeling is really fundamental. It's maybe as fundamental when around 1980, GCM reached 100 kilometer horizontal resolution. For the first time, we were able to appropriately represent quasi-horizontal motions, really motions on isentropic surfaces in low-pressure systems and cold front. And this led to this revolution, which is sometimes referred to as the quiet revolution of numerical weather predictions. I think in this decade, the resolution will reach about 1 kilometer. This allows an appropriate representation of vertical, meaning across isentropic motions. And it removes 2 critical parameterizations and improves representation of hydrological cycle and extremes. Of course, the remaining question, will this target 1 kilometer global reduce the uncertainty of climate projections? I think we do not really know, we cannot tell, but I think we should try, we must try. Thanks a lot.
Many thanks, fantastic. And honestly, I messed up a bit. I think we now only have order of 7-8 minutes for discussion. My mistake, I'm sorry. But I think still that will allow for, I don't know, some 4 or so questions, which I invite now. Wait for the microphone, please. Sorry, ladies first.
Hello, thanks a lot for this impressive talk. My name is Jennifer Brauch. I'm from the DWD. Just for your last slide, you said you have 16 years for this one simulated year per day, and this is now reduced to 1 decade with the Exclaim project. Is that right?
Yes, so we think that if we actually exploit this process or in a better way than we're able to do in the past, this will give us a substantial speed up. And so we think that within 6 years, that is the goal of this project, we can reach this 1 kilometer global with a simulated year.
Okay, but for my opinion, this is only the one part of the story, because the other part is you create a huge amount of data.
Yeah.
So, and you have to store, you have to manage, you have to look at, you have to validate, you have to tune, and this might also take another 10 years. And so we are, I don't know. So
yeah,
it's not really a question; it's just a statement.
Yeah, well, it's a good point, Jennifer. But actually, there are ways how one can look that. We have actually developed a tool where we do not store the data anymore. So where one really does online analysis in a convenient form, and we have described this actually in our BAMS paper. And of course, that would need to be further developed. But I think in the end, maybe we will not store all the data as we did in the past, but only a subset of the data. For instance, we can actually, and we do this already now, even if we require high-resolution data, we store the data only at every second grid point. And that already makes a factor 4 in volume. So there are ways how one can reduce the storage, the data avalanche.
Christoph, well, my congratulations for a very nice talk with contemporary history of the computing, Zeitgeschichte. My question to you is links to yesterday's keynote. I think you are very aware of the situation in Switzerland, a smaller country, and you are a central figure. And if you're looking to the demands which Daniela Jakob mentioned, you know what the society looks about, and how is it regarded in what kind of personal impression do you have? Do the stakeholders, as they're called, listen to those sort of results, or is it basically academic interest, with your flood of papers from your group? Could you comment on that?
Well, if I look at what happens in Switzerland, or the country that I'm very aware of, their climate change program, UK Met Office, for instance, but also Germany, then I think these new simulations, they are being picked up rapidly by the climate change community to develop national or regional climate change scenarios, which can then be used in climate change adaptation. I think one point that maybe is not taken or understood sufficiently in the public is really the large uncertainty that we still have because of limited representation of clouds, for instance. And that is, of course, a key uncertainty which addresses every point on the planet. So whether we have a global warming of 2 degrees or 4 degrees or 5 degrees or 6 degrees, all in the ballpark of the possible, makes a fundamental change for climate change at any location. And so that is one of the targets that is independent of providing user-oriented information about extreme events. Yeah. Thanks for your question.
Hello. Can you hear me? All right. Helge Knob is my name. I have a question. You talked in the end about the domain-specific languages being a solution. How mature are these languages today?
Can you repeat? I didn't get the last.
How mature are these domain-specific languages today in terms of solving the problems that are solved manually right now?
Yeah, so this is part of this Exclaim project. So actually the big thing now is that they appear to work well for regular grids, where we can number our grid points with I and J and K. Yeah, but in the more general form, how one solves the equations today in ICANN or IFS-FVM, one will use unstructured meshes. And so a big plan or a big part of the future development is to make available these domain-specific languages for unstructured grids. And that is actually what is going to happen. So in this sense, I think one can say one is not yet really at the point, but actually the FV3 model, which is one of the 3 which uses a cubed sphere, already runs in a Python-based DSL implementation. So there are promising signals from recent work.
There's also a couple of questions from the GatherTown chat, and maybe we approach them chronologically. Elias Zubler asks, can you say something about the progress made with respect to modeling low stratus, Hochnebel, in the Swiss plateau in CRMs?
Okay, yeah. Hi Eli, nice to hear from you. Yeah, so I know that some work is being done. So this is well, the people in Switzerland know it. We sometimes get the stratus cloud, which is not always forecasted. And and which of course is a very important factor for our tourism, because whether you are above the stratus or below makes a big difference in your experience of the Sunday. Yeah, and so I know that there is some work going on actually at Meteor Swiss, and it has a certain role appears to be played by terrain following coordinate formulations, but I don't think that the problem has fully been solved.
Okay. There's another question by Heinke Schlünzen, which is a short one, but probably not so easy to answer, is how is the theoretical resolution improved?
How is
theoretical resolution improved?
Not sure whether I get it.
Maybe Heinke Schlünzen can elaborate on the question, and we go to the next one, which is from Leo Jung-Andreas. And he asks, you are normally using Cosmo, if I understand it correctly. Is Cosmo in this mode fully coupled, or do you then plan to switch to Icon if you are successful with the Exclaim project?
Yeah, well, I'm glad for this question, yeah. Well, of course, we try to get rid of Cosmo, as everybody does, as soon as we can, but in the moment it's still much faster than Icon. And so it's still a good workhorse tool for us to explore what we hopefully will be able in a few years with Icon.
Okay, maybe a last one from Martin Klein. How problematic is the modification of SGS parameterizations, especially for the surface layer for higher resolutions?
Yeah, so we did some work with that in the studies of Davide Panosetti, where we looked at convergence. So I think it's something we have to look into, but in our simulations we didn't see that we are forced to use LES even at scales of about 1 kilometer. So I think at 1 kilometer we can go by having basically vertical turbulence, 1D turbulence. Yeah.
If I may, since I have the microphone, elaborate on Leonora's question. You talked about the atmosphere. You also talked a bit about soil moisture. What about the ocean?
Yeah, so within the Exclaim project, we also address the ocean. So Nicky Gruber is an oceanographer. He's leading the Exclaim project, so he will make sure that we deal with the ocean as well. And because the ocean, the ocean code primarily consists of the dynamical core. The atmospheric code is much more complicated. So we think actually that the ocean code can easier be translated to a domain-specific language, the same actually, than the atmosphere.
Yeah, thank you very much indeed again for the discussion. And yeah, I think that's appropriate indeed. Yeah, thank you. So we now have the time to move to the two other lecture halls in case we want to. Of course, the polar session is also fascinating. I guess I'm going to stay here. And then be reminded at the beginning of the break, there will be the weather prediction by our colleagues from the Leipzig branch of the German Meteorological Service, so you can see how the weather develops.